Okay, this chapter is going to talk about techniques of integration. So we're going to start in this first section here about some basic integration techniques. Remember that if you integrate a function using the chain rule, say you have f evaluated g of x times g prime of x dx. That's generally, another way to say that is if you integrate that, that's the same as saying if you integrate f of u du, then those two integrals are actually equal to one another. So since this is a calculus 2, I'm going to assume that you have already discussed many of the basic integration formulas. So for instance, you know that if you just integrate du, you'll get u plus c. Now remember, anytime I say u is a function of x in most cases. If you integrate a constant du, then that would equal the constant times the function plus another constant. And of course, you have the sum property that if you integrate the sum of an integral du plus dv, then that's going to equal the integral of du plus the integral of dv. And actually that's true for functions as well. So if you had f of u du plus f of v dv, that would integrate to the integral of f of u du plus the integral of f of v dv. And then you have the general power rule here, that if you integrate u to the n du, you get u to the n plus 1 over n plus 1 plus c. And then we have the log rule, that when you integrate du over u, you get the natural log of the absolute value of u plus c. And of course, if the u value can never be negative, you could actually remove the absolute value. And then we have the formula for e to the u du, which is equal to e to the u plus a constant. And then if the exponential if the base of the exponent is a number other than e, like a to the u du, we have a formula for that. So that would just integrate to a to the u times the natural log of a plus a constant. Then we get into our trig integrals, and you know that if you integrate the cosine of u du, that's just going to integrate to sine of u plus a constant. And then if you integrate sine u, that's going to integrate to minus cosine of u plus a constant. And if you integrate secant squared u, that's going to integrate to tangent u plus a constant. If you integrate cosecant squared u, then that's going to integrate to minus cotangent u plus a constant. And if you integrate secant u tangent u, that's going to integrate to secant u plus a constant. And then the last two, if you integrate cosecant u cotangent u du, that integrates to minus cosecant u plus a constant. And then I'll talk about 14 next, but those 6 that I just covered there, those actually were derived because you knew what the derivatives of certain functions were. For instance, you knew the derivative of tangent u was secant squared u, so therefore when you integrate secant squared u, you're going to get tangent u plus a constant. Now these others, we had to develop them using other techniques, but we were able to get formulas for these. The integral of tangent u du is actually, there's 2 ways you can represent it. You can represent it as minus the natural log of the absolute value of cosine u plus a c, or you can represent it as the natural log of the absolute value of secant u plus c. And then the same thing for the integral of cotangent u. That can be minus the natural log of the absolute value of cosecant u plus a constant, or the natural log of the absolute value of sine of u plus a constant. And so that pretty much covers all of our trig functions. And the next one, I may be giving you these a little bit earlier than needed, because I actually do cover a section on hyperbolics, but I'm going to go ahead and give you these in case you've covered them. If you integrate the hyperbolic sine of u du, then that would equal the hyperbolic cosine of u plus a constant. And if you integrate the hyperbolic cosine of u du, then that would equal the hyperbolic sine of u plus a constant. And if you don't know what those are, don't worry about them for now. Alright, and there's also some integrals that actually lead to inverse trig functions. So if you were to integrate du over the square root of a squared minus u squared, that integrates to the arc sine of u over a plus c. And then if you integrate du over a squared plus u squared, then that integrates to 1 over the arc tangent of u over a plus a constant. Then if you integrate du over u times the square root of u squared minus a squared, that integrates to 1 over a times the arc secant of the absolute value of u over a plus a constant. And then if you have the integral of du over the square root of a squared plus u squared, that's actually going to be the integral of, that's going to equal the inverse hyperbolic sine of u over a plus a constant if a is greater than 0. And if you integrate du over the square root of u squared minus a squared, then that's going to be the inverse hyperbolic cosine of u over a plus a constant. And there are some conditions that have to be satisfied here, but we won't worry about those now. So again, those last two, if you haven't talked about hyperbolic sines or hyperbolic cosines, don't worry about it. Toward the end of this chapter, we'll actually discuss those. So let's take a look at some of these examples. First, we'll start with this one. If I wanted to integrate this, what we could do is we could let u be the denominator, and since the denominator is not raised to a power, I could try to get this in the form of the integral of du over u. So let's see what du is. Du would be 2t minus 1 dt. So this one's going to work out perfectly. The numerator, 2t minus 1 dt, is du, and then the denominator is going to be u. So when you integrate du over u, you get natural log of the absolute value of u plus a constant. And now we just replace u with our substitution. So we get natural log of the absolute value of t squared minus t plus 1 plus a constant. Okay, and then here, this one we can do with the using a trig. This is actually a trig integral, because if we let's say we let u be 3x, then du would be 3dx. Now we're going to have to manipulate this, and so what we would have to do to manipulate this is we would have to put a 1/3 out here, and then we would have to put a 3 on the inside. Okay, so what that would do is that would leave me with this 1/3 outside the integral, and then the 3 dx here. If you put the 3 and the dx together, that's actually the du, and then the secant 3x and the tangent 3x is actually the secant u tangent u. So when you integrate secant u tangent u, you just get secant u. So we would have 1/3 secant u plus a constant, and then replace u with the substitution. U is 3x, so you'd have 1/3 secant of 3x plus a constant. Okay, here's a definite integral, but I actually didn't finish that. So let's just go ahead and say that this is, or I'll go ahead and finish it in a minute here. But let's assume it's an indefinite integral for now. So you have cosine of x times e to the sine of x. So you could let u equal sine of x, and then du would simply be the derivative of that times dx, cosine x dx. So this part right here, the cosine x and the dx, are actually the du, and then e to the sine of x is e to the u. So you're actually integrating e to the u du, and the formula says e to the u du is e to the u plus a constant, and since u is sine x, that's e to the sine x plus a constant. Now, if you wanted to go ahead and evaluate this this integral, the definite integral portion of it, you wouldn't need the constant, and so you would evaluate this from 0 to pi. And so let's see, you would get e to the sine of pi. So what would the sine of pi be? Sine of pi, wouldn't that be 0? So the sine of pi would be 0, so you get e to the 0. Okay, so I did this a little bit neater here. So e to the sine of pi would be e to the 0, and then of course the lower limit is 0, so you'd have e to the 0. So basically you'd have e to the 0 minus e to the 0, which is 0. Now the next one here is a power rule problem, because this is actually the cosine of x down here raised to the 1/2 power. So you can actually think of this, if you moved it in the numerator, it would be cosine to the negative. It would be cosine to the negative 1/2 power. So what we can do is we can let u equal cosine of x, and then du would be minus sine x dx. So what we'd have to do is put a minus right here, and then put a minus right here. And then the minus sine x dx, that's the du. And then having 1 over the square root of cosine x, remember that's the same as cosine x raised to the negative 1/2 power. So that would be, since u is cosine x, that would be u to the negative 1/2 power. And then when you integrate this, you add 1 to this, and so you get u to the 1/2 power divided by a half. When you divide by a half, you multiply by 2. So with the negative, we have negative 2u to the 1/2 plus c. And then we can replace u with the cosine x. So we have minus 2 times the cosine x to the 1/2 power plus a constant. And then, cosine x to the 1/2 power is just the square root of cosine x. Now on this one, I'm going to complete the square. So watch what I do here. I'm going to take this trinomial. First thing I'm going to do is factor a 4 out of each term. So that's going to leave me with x squared minus 2x plus 3/4. Then I can complete the square. So if I take half of negative 1 and square it, that would give me 1. So I can add 1 to x squared minus 2x, and that would give me a plus 1 there. And then I have to take away 1 from the 3/4. Now if you're wondering where the 4 went, I took that out of the radical because the square root of 4 is 2. So I put that outside the radical. Now this is now x squared minus 2x plus 1 can be written as x minus 1 quantity squared, and 3/4 minus 1 is negative 1/4. So now I will have, if I let u equal x minus 1, then I have 1 over u right here times the square root of u squared. That should be a 2 there. Okay, so times the square root of u squared minus 1/2 squared du. So now I have a 1/2. That came from the 2 that I had in the denominator. So pull the 1/2 out here, and I have 1/2 times the integral of 1 over u times the square root of u squared minus 1/2 quantity squared. And we learned earlier that this integral here integrates to 1 over a, and a is a half, arcsecant of absolute value of u over a. And so if we simplify this, this is 1/2 times 2, which is just 1, so those just cancel. Those cancel out. So you end up with the arcsecant of the absolute value of u, and since u is x minus 1, we would put that in there, and since you're dividing it by a half, you could put the 2 back in the numerator there, and so you get arcsecant of 2 times the absolute value of x minus 1 plus a constant. Okay, now I'm going to finish this video. I'm going to do the second half of this on another video, and I'm going to work some more of these basic integral problems.